When we use the McCabe-Thiele method to determine the number of equilibrium stages in a distillation column, we end up with this equation that relates Y, the vapor mole fraction, X, the liquid mole fraction, to Q, where Q is the quality as defined for a distillation column. It's the fraction of the liquid in the feed. So if Q equals 0, we have saturated vapor, meaning we're right at the dew point. And if Q is 1, it's saturated liquid, right at the bubble point. And then Q between 0 and 1 means we have a mixture. So what we want to do in this screencast is explain where this equation comes from. So the other term in the equation is ZF, and that's the mole fraction of the feed, which for this example is here. So let me show you the diagram, the Y versus X. The mole fraction of the feed in this case is 0.5, and we're going to look at a case where in this diagram on the right we feed a quality somewhere between 0 and 1. So this means some of the feed goes into the liquid phase, which is flowing down. So this is the molar flow rate of liquid, molar flow rate of vapor in the rectifying section. And then we use the symbol L bar for the molar flow rate here and V bar. So you can see that L bar would be the liquid that's flowing down plus what we add from the feed. So the fraction that's liquid in the feed goes down, and likewise V would be V bar plus the remaining fraction, which was vapor, that's flowing up. So in the diagram for McCabe-Thiele, we have two operating lines. This one, and we've derived these equations, explained them in other screencasts. So I'm just going to relate to the liquid and vapor flow rates in that region, and then the distillate mole fraction and the distillate molar flow rate. And for the stripping line, operating line, we have the volumetric flow rate in this region. Again, that's liquid flow rate minus the bottom's mole fraction times the molar flow rate out of the bottom of the distillation column. So I'm going to copy these equations over here on the right. So keep in mind these two equations came from mass balances, top part of the column and the bottom part of the column. If I were to look at the point where they intersect, in other words, where they have the same X and Y values, I could subtract the two equations, and now we have the same Y value, and likewise L minus A bar the same X value. All right, so I have distillate flow rate, and then because we're subtracting these equations, this becomes plus sign. So notice that the terms V minus V bar is equal to 1 minus Q times the molar flow rate of feed. So I can make that substitution, 1 minus Q, molar flow rate of feed times Y. And then here, L minus L bar is equal to minus Q times F. So this becomes minus Q F times X. And now let's look at these last two terms. Let me go over here and try to write an overall balance for the more volatile components. So it's coming in, the entire column. It's coming in and it's leaving in the distillate or in the bottoms. And so notice this two terms on the right. So that means I can make this substitution. And then, since F appears in all the terms, I can drop that out of the equation, and then I can rearrange it. So this is the equation that we originally wanted to derive for that line, Q line. And so this then is the slope of that line. If X is equal to ZF, if you look at this equation, it turns out Y is equal to ZF. That means this is, of course, a point on that Q line.